An object moves 5 meters right, then 5 meters back. Total distance, 10 meters. Displacement, 0. Average velocity, also 0. Velocity depends on displacement, not distance. And that's where careful physics begins. This video traces how average velocity over a time interval becomes instantaneous velocity through the limit, giving us the derivative of position. The x component of average velocity is defined as displacement divided by the time interval. We write v sub a equals delta x over delta t. For one-dimensional motion, we drop the x subscript, since there's only one spatial component to track. Later, when we study two-dimensional motion, the subscripts return to distinguish horizontal and the vertical components. The average velocity vector is v sub of times I hat, directed along the x-axis. The SI unit is meters per second. Displacement means final position minus initial position, assigned quantity. Positive displacement means the object moved in the positive x direction. Negative displacement means it moved the other way. A common misconception: average velocity equals distance traveled divided by time. It does not. Imagine an object that moves 3 meters in the positive x direction, then reverses and moves 3 meters back. Total distance traveled, 6 meters. Net displacement 0, the object returned to its starting point. If this round trip took 2 seconds, the average speed is 3 meters per second, but the average velocity is 0 divided by 2 seconds, 0. Displacement captures net change in position, and that's what average velocity measures. On a position versus time graph, average velocity has a direct geometric meaning. Pick 2 points on the curve, the point at time t with position x of t, and the point at time t plus delta t with position x of t plus delta t. Connect them with a straight line, a secant line. The slope of that secant is rise over run, the change in position delta s divided by the change in time delta t. That slope is the average velocity over the interval. A steep secant means large average velocity. A horizontal secant means zero average velocity. A downward sloping secant means negative average velocity. Now shrink that time interval, hold the starting point fixed at time t, and slide the second point closer. As delta t decreases, the secant pivots. With progressively smaller intervals, the secant lines converge towards the tangent to the curve at time t. The tangent slope is the instantaneous velocity. V of t equals the limit as delta t approaches 0 of x of t plus delta t minus x of t divided by delta t. This limit is the derivative dx over dt. The instantaneous velocity vector is v of t times I hat. The sign of v of t indicates direction, positive for motion in the positive x direction, 0 at rest, negative for motion the other way. Consider an object with position x of t equals x naught plus 1/2 bt squared, where x naught is the initial position at time 0. We derive the instantaneous velocity directly from the limit definition of the derivative. First, evaluate x at time t plus delta t. Substitute into the position function, x of t plus delta t equals x naught plus 1/2, b times the quantity t plus delta t squared. Now expand the square. The quantity t plus delta t squared equals t squared plus 2t delta, t plus delta t squared. So x of t plus delta t equals x naught plus 1/2 b times the quantity t squared plus 2t delta t plus delta t squared. Now form the displacement. Delta x equals x of t plus delta t minus x of t. Substitute both expressions. X naught plus 1/2 b times t squared plus 2t delta t plus delta t squared minus x naught minus 1/2 bt squared. The x naught terms cancel. The 1/2 bt squared terms cancel. What survives is 1/2 b times the quantity 2t delta t plus delta t squared. Simplify this to bt times delta t plus 1/2 b times delta t squared. Now divide by delta t to form the difference quotient. Each term has a delta t factor, so delta x over delta t equals bt plus 1/2 b delta t. Now take the limit as delta t approaches 0. The first term, bt, is independent of delta t, so it stays. The second term, 1/2 b delta t, shrinks to 0. The instantaneous velocity is v of t equals bt. This result came straight from the limit definition, the definition that underlies every derivative in calculus. The position function was quadratic in t, and the velocity turned out linear. Plot v of t against time, a straight line through the origin with slope b. At time 0, the velocity is 0, so the object starts at rest. As time increases, the velocity increases at the constant rate b. Now consider a more general position function. X of t equals x naught plus v naught times t plus 1/2 bt squared. The constant v naught is the initial velocity, and the b controls how velocity changes over time. On a position time graph, this traces a parabola. Take the derivative to find instantaneous velocity. V of t equals v naught plus b times t. Velocity is linear in time. Now compute the average velocity over the interval from t sub I to t sub f. The displacement is delta x equals x of t sub f minus x of t sub I. Expanding, delta x equals v naught times the quantity t sub f minus t sub I plus 1/2 b times the quantity t sub f squared minus t sub I squared. Factor the difference of squares. T sub f squared minus t sub I squared equals t sub f minus t sub I times t sub f plus t sub I. The displacement becomes delta x equals t sub f minus t sub I times the quantity v naught plus 1/2 b times t sub f plus t sub I. Divide both sides by t sub f minus t sub I. The average velocity is v sub f equals v naught plus 1/2 b times the quantity t sub f plus t sub I. The mean value theorem from calculus guarantees that some time t1 exists between t sub I and t sub f, where the instantaneous velocity equals the average velocity. On the graph, the tangent at t1 has the same slope as the secant connecting the endpoints. Set v of t1 equal to v sub f, v naught plus b times t1 equals v naught plus 1/2 b times t sub f plus t sub I. Cancel v naught. Divide by b. The result, t1 equals t sub f plus t sub I all over 2. The midpoint. Now evaluate the velocities at the endpoints. V at t sub I equals v naught plus b times t sub I. V at t sub f equals v naught plus b times t sub f. The arithmetic mean of these two is v at t sub I plus v at t sub f divided by 2. Expand, this equals v naught plus 1/2 b times t sub f plus t sub I, identical to v sub f. Here is the key distinction. The arithmetic mean of the endpoint velocities equals the average velocity in this case. But this holds only because v of t is linear in t. For any nonlinear velocity function, the arithmetic mean of the endpoint velocities will not match the true average velocity. These are fundamentally different concepts that coincide only in the linear case. From here on, average velocity means one thing: displacement divided by time interval. 3 results to carry forward. Average velocity is displacement over time, the slope of the secant line on a position time graph. Instantaneous velocity is the limit of that ratio as the interval shrinks to 0. The slope of the tangent line equal to the derivative dx over dt, and the arithmetic mean of endpoint velocities equals the average velocity only when velocity is a linear function of time. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.